Right now, a wave of videos and headlines are circulating with some version of this claim, that the James Webb Space Telescope has detected a mysterious signal originating from beyond our solar system. Language dramatic enough that it's easy to picture something like a radio broadcast, a deliberate transmission, or some kind of technological beacon, reaching us from deep space. Before going any further, it's worth being precise about what that word signal actually refers to here, because the real story is genuinely remarkable on its own terms, without needing any embellishment. James Webb has not picked up anything resembling a radio transmission or an artificial broadcast. What it has detected is a chemical signal, a precise pattern of light coming from an actual physical object passing through our solar system right now, an interstellar comet called 3I Atlas, only the third confirmed visitor from beyond our sun's own neighborhood ever recorded in the history of astronomy. And the specific signal Webb picked up turns out to be genuinely strange enough that scientists are still working through exactly what it means. This has been unfolding across the better part of a year now, in stages, as multiple different Webb observation campaigns have gradually built up an increasingly detailed picture of exactly what this object is made of. Let's go through this phase by phase, because the story of what Webb actually detected and how it detected it says as much about the extraordinary sensitivity of modern space telescopes as it does about the object itself. According to the Minor Planet Center, 3I Atlas was officially discovered on July 1st, 2025. By the Asteroid Terrestrial Impact Last Alert System, a network of robotic telescopes designed to continuously scan the sky for exactly this kind of fast-moving object. The name breaks down simply enough. The 3I marks it as the third confirmed interstellar object ever detected, following 1I Oumuamua in 2017 and 2I Borisov in 2019. What immediately set it apart from an ordinary solar system comet was its trajectory. Rather than looping around the sun on a closed elliptical orbit the way virtually every native comet does, 3I or Atlas is moving on a hyperbolic path, the unmistakable signature of an object not gravitationally bound to our sun at all. It arrived from interstellar space. It made its closest approach to the sun in October of 2025. And having already passed that point, it is now on a permanent one-way trip back out into the galaxy, never to return. The signal at the center of all this recent coverage is, specifically, a spectroscopic signal, and it's worth explaining exactly what that means, since it's the single most important concept for understanding everything Webb has actually found. A spectrograph, the type of instrument responsible for these detections, works by spreading incoming light out across its full range of wavelengths, similar to how a prism splits sunlight into a rainbow, except far more precisely and across wavelengths well beyond what the human eye can see. Every chemical element and molecule absorbs and emits light at extremely specific, well-cataloged wavelengths, effectively leaving behind a unique fingerprint in that spread-out light. By analyzing precisely which wavelengths are missing, brightened or otherwise altered in the light coming from an object like 3I Atlas, scientists can determine exactly which molecules are present in the gas and dust surrounding it, without ever needing to physically sample the object itself. That is the entire meaning behind headlines describing a detected signal. Not a broadcast, but a chemical fingerprint encoded directly in light that has traveled hundreds of millions of miles before ever reaching Webb's detectors. The first of these signal detections came on August 6, 2025, when Webb turned its near-infrared spectrograph, known as NER-SPEC, toward 3I Atlas for the very first time. According to NASA's science team, that initial observation returned a genuinely striking result. A coma, the diffuse cloud of gas and dust surrounding the comet's solid nucleus, dominated overwhelmingly by carbon dioxide rather than the water vapor that typically dominates comets native to our own solar system. The measured ratio of carbon dioxide to water in that coma came out to roughly 7.6, among the highest such ratios ever recorded in any comet studied to date, sitting more than 4.5 standard deviations above the trend line researchers would normally expect for an object at that particular distance from the sun. Alongside that dominant carbon dioxide signature, Webb's instruments also picked up water, carbon monoxide, water ice, fine dust particles, and a tentative, not yet fully confirmed signal consistent with a sulfur-bearing compound called carbonyl sulfide. Then months later, after the comet had already made its closest approach to the sun and begun its outbound journey back toward interstellar space, Webb returned for a second, considerably more detailed look, this time using an entirely different instrument. According to a paper led by Caltech, astronomer Matthew Belyakoff and colleagues published in April of 2026 in the astrophysical journal Letters, Webb's mid-infrared instrument known as MIRI captured what researchers describe as the very first mid-infrared chemical fingerprint ever collected from any interstellar object. Observing 3I Atlas on two separate dates in February of 2026, MIRI picked up a genuinely New signal that NIR SPEC's earlier observation had not been able to detect. A clear, unambiguous signature of methane gas escaping from the comet, marking the first time methane has ever been directly detected on an interstellar visitor. Alongside that methane detection, the MIRI observations also mapped out precisely where different gases were concentrated around the comet, finding that water vapor spread out across a comparatively broad area, since much of it was being released from icy grains scattered throughout the surrounding coma, while both carbon dioxide and methane stayed considerably more concentrated close to the comet's actual nucleus. That distinction in where different gases were physically located turned out to carry real scientific weight. According to the research team, the fact that carbon dioxide and methane were both found clustered tightly around the nucleus itself, rather than spread diffusely throughout the coma the way water was, suggests those two particular gases may be venting more or less directly from the comet's solid surface, offering a comparatively direct window into the actual composition of the object's core, rather than reflecting some secondary process happening further out in the surrounding cloud of dust and ice. The MIRI observations also tracked how the intensity of that chemical signal changed as the comet continued moving away from the sun between the two observation dates, finding a sharp decline in overall gas production, with water showing the single most pronounced drop of any of the detected molecules. Researchers involved in the study described the pattern as expected behavior for an object like this, since as the comet receives less heat from the increasingly distant sun, its surface grows colder and progressively less ice gets vaporized into the surrounding coma, gradually quieting the very signal Webb had been tracking. It's worth explaining why this particular combination of chemical signals, especially that unusually high carbon dioxide to water ratio and the clear methane detection, matters so much to scientists beyond simply being an interesting curiosity. Comets are essentially frozen time capsules, chunks of ice, dust, and rock that formed early in the history of whatever planetary system produced them and have remained largely unchanged ever since, preserved by the deep cold of space. Studying the precise mix of ices and volatile compounds locked inside a comet's nucleus offers a direct window into the chemical conditions present at the exact time and place that comet originally formed, potentially billions of years ago, and, in the case of an interstellar visitor like 3I Atlas, in an entirely different star system altogether. According to researchers involved in this analysis, comparing the specific ratio of water ice to carbon dioxide, ice measured in an interstellar object, against the same ratio found in native solar system comets, offers a direct way to gauge whether the distant unknown planetary system, 3I and Atlas, came from shared broadly similar formation conditions to our own solar systems, or whether it developed under dramatically different conditions entirely. Webb's chemical fingerprinting has not been the only spectroscopic effort directed at 3I Atlas either, and comparing its results against separate independent observations helps confirm just how unusual this object's composition genuinely is. A complementary study using the European Southern Observatory's Very Large Telescope in Chile, led by astronomer Cyrielle Opetom of the University of Edinburgh, analyzed rare, isotopic varieties of carbon and nitrogen present in the comet in the form of cyanide compounds, a completely different class of molecule from anything Webb specifically targeted. That research adds a separate, independent layer of chemical detail to the overall picture Webb has been building, and researchers involved describe the combined data set as offering a genuine window into the possibilities of prebiotic chemistry occurring elsewhere across the galaxy, the basic chemical building blocks that, under the right conditions, can eventually contribute to the ingredients life requires. Though detecting those building blocks in a comet's coma is a very different and far more modest claim than detecting any actual signature of life itself. Based on these specific chemical signals detected across both of Webb's observation campaigns, along with detailed modeling of the object's likely formation environment, researchers have proposed that 3I Atlas may be extraordinarily old, on the order of 10 to 12 billion years, a figure that, if accurate, would make it considerably older than our entire solar system, which itself formed roughly 4.6 billion years ago. An object that ancient would have condensed out of material present during the universe's comparatively early history, meaning the star system 3I Atlas originally formed within may no longer even exist in any recognizable form. Today, having long since evolved, dispersed, or been fundamentally altered over the many billions of years since 3I Atlas itself first coalesced into a solid object, and was eventually flung out into interstellar space, likely through some ancient gravitational encounter with another passing star or planet within its birth system. It's worth being direct about why this particular signal has generated such an unusually intense wave of public fascination and, in some corners of online discussion, genuine speculation about something considerably stranger than an ancient comet. 3I Atlas's combination of extreme speed, its highly unusual chemical composition, and the sheer novelty of being only the third, confirmed interstellar object ever detected has made it a magnet for speculation, extending well beyond mainstream scientific consensus. Most prominently, Harvard astrophysicist Avi Loeb, who has a documented history of proposing that unusual interstellar objects, including the earlier visitor Oumuamua, might be artificial in origin rather than natural, has publicly raised similar questions about 3I Atlas, pointing to aspects of its trajectory and its unusual outgassing behavior as at least worth considering alongside more conventional explanations. It's important to be clear that this view remains a distinctly minority position within the broader astronomical community. The overwhelming majority of researchers studying 3I Atlas, including the teams behind both of Webb's spectroscopic observation campaigns, treat it as a genuine, if chemically unusual, natural comet, an ancient icy body from another star system behaving according to well-understood cometary physics, rather than anything artificial. The carbon dioxide-dominated coma and the methane detection are both entirely consistent with natural cometary outgassing, simply reflecting a genuinely different and genuinely informative set of formation conditions from what produced the comets native to our own solar system. It's worth explaining what a genuine technosignature search actually looks like in practice, since the contrast helps clarify exactly why 3I Atlas's chemical spectrum doesn't belong in that category. Programs like Breakthrough Listen, which uses large radio telescopes to scan nearby star systems for artificial radio transmissions, or projects that search visible light for unusual, precisely repeating flashes that couldn't plausibly occur naturally, are built specifically to detect signals with characteristics that clearly distinguish them from anything produced by ordinary astrophysical processes, sharp, narrowband radio frequencies, for instance, rather than the broad, smoothly varying spectral features typical of natural gas and dust. Nothing Webb recorded from 3I Atlas shows any of those characteristics. Every spectral feature identified in its coma, the carbon dioxide, the water, the methane, sits exactly where well-established laboratory measurements say those specific molecules should appear when heated and vaporized under natural conditions, matching the same broad, gradually sloping spectral shapes produced by comets throughout our own solar system, just in an unusually different overall ratio. That distinction matters enormously when it comes to correctly understanding what Webb actually detected, because the word signal, stripped of its scientific context, invites exactly the kind of confusion that has fueled so much recent speculative coverage. There's a real, important, and active field of astronomy dedicated specifically to searching for genuine technosignatures, deliberate or incidental signs of technology produced by an intelligent civilization elsewhere in the universe, whether that's an artificial radio transmission, an unusual pattern of light, or some other engineered signature that couldn't plausibly arise from natural processes alone. Nothing Webb detected from 3I Atlas falls into that category. Every molecule identified in its coma, carbon dioxide, water, carbon monoxide, methane, and the tentative carbonyl sulfide signal is a naturally occurring compound commonly found throughout the universe, produced by entirely ordinary physical and chemical processes. The same basic categories of ice and gas found in comets throughout our own solar system, just present in an unusually different ratio than researchers had previously observed. What makes Webb's specific involvement in this story so significant is a matter of instrumentation and timing, rather than anything mysterious about the signal itself. 3I Atlas is only passing through our solar system briefly, because it's moving on a hyperbolic trajectory rather than a closed orbit. This is the only opportunity astronomers will ever have to study it up close before it disappears permanently back into interstellar space. Webb's specific combination of infrared sensitivity and spectroscopic precision makes it uniquely capable of resolving the kind of fine chemical detail needed to identify individual molecules in a comet's coma from tens of millions of miles away, a capability that simply didn't exist for either of the two previous interstellar objects detected before Webb ever launched. Oumuamua, discovered in 2017, was gone from view before any sufficiently powerful infrared telescope could be brought to bear on it in detail, leaving its true composition still genuinely uncertain to this day, a gap in knowledge that fueled years of ongoing scientific debate, and, notably, much of the same speculative artificial origin discussion that has since resurfaced around 3I Atlas. Without a clear chemical signal to point to, Oumuamua's strange, elongated shape and its unusual acceleration as it left the solar system, a subtle push that couldn't be fully explained by gravity alone, left researchers working largely from incomplete data, proposing explanations ranging from unusually pure hydrogen ice to normal cometary outgassing, too faint to detect with the instruments available at the time. That unresolved uncertainty is a direct consequence of not having anything comparable to Webb's spectroscopic capability available during Oumuamua's brief visit. and it stands as a useful illustration of exactly how much scientific value a detailed chemical signal like the one captured from 3I Atlas actually provides, simply by removing that same kind of ambiguity from the conversation entirely. Borisov, discovered in 2019, was studied with a range of ground-based instruments that provided useful but considerably less detailed chemical information than what Webb has now been able to extract from 3I Atlas. It's worth understanding a bit about why Webb specifically is capable of this kind of precise chemical fingerprinting in the first place, since the underlying engineering is itself a genuine feat. James Webb sits roughly 1 million miles from Earth, at a gravitationally stable point in space known as the second Lagrange point, far enough from the heat of Earth, the Moon, and the Sun that its tennis court-sized sunshield can keep its infrared instruments cold enough to function at all. MIRI, the instrument responsible for the methane detection, has to be cooled even further than the rest of the observatory, down to around 7 Kelvin, just a few degrees above absolute zero, using a dedicated mechanical cryocooler, because detectors sensitive enough to pick up the faint infrared glow of gas escaping a comet hundreds of millions of miles away would otherwise be completely swamped by the telescope's own residual warmth. That extraordinary sensitivity is exactly what allowed Webb to resolve subtle differences in where different gases were physically concentrated around 3I Atlas's nucleus, a level of detail that would have been utterly unreachable for any telescope built even a decade or two earlier. That difference in observational capability is precisely why 3I Atlas has become, by a wide margin, the best characterized interstellar object in the short history of this entire category of astronomical discovery. Beyond Webb, the object has also been studied using the Hubble Space Telescope, which captured detailed imagery of the comet in late November of 2025, as it continued its outbound journey, by NASA's Mars Reconnaissance Orbiter, which photographed it during its passage through the inner solar system, and by the European Space Agency's newer Sphere-X mission, adding yet another independent line of data to the overall picture. Researchers have also gone back through archival data and discovered that the Vera C. Rubin Observatory in Chile, still in its pre-launch commissioning phase at the time, had actually captured images of 3I Atlas as early as June 21st, 2025, a full 10 days before the object's official discovery announcement, an almost accidental early detection that has become one of the more charming footnotes of the entire saga. That accidental early detection points toward something significant about how future interstellar visitors are likely to be found and studied going forward. Now that Rubin Observatory has officially begun its full 10-year survey, continuously imaging enormous swaths of the sky and comparing each new image against everything captured before it, astronomers expect the observatory could realistically identify several additional interstellar objects over the coming decade, transforming what has, until now, been an exceedingly rare category of discovery, just 3 confirmed objects across the entire history of astronomy, into something considerably closer to a routine, recurring event. If that projection holds, Webb's role in this particular story may end up serving as a template for how future interstellar visitors get studied as well. A wide-field survey instrument like Rubin casting an enormous net capable of catching the next unusual visitor the moment it enters our solar system, paired with Webb's precise spectroscopic follow-up capability standing ready to extract exactly the kind of detailed chemical signal that transformed 3I Atlas from a fast-moving point of light into one of the most thoroughly documented objects of its kind in the short history of interstellar object science. It's worth stepping back to consider the broader research effort this represents, because the sheer scale of coordinated observation focused on a single temporary visitor is itself a genuinely notable achievement in modern astronomy. According to NASA's own public updates on the mission, the agency has specifically emphasized that a host of different missions are coming, together to observe 3I Atlas, precisely because it is only passing through, using every available tool before it disappears back into the cosmic dark for good. That kind of rapid, coordinated, multi-instrument response, mobilizing some of the most advanced telescopes ever built to study any object discovered essentially without warning, reflects just how seriously the astronomical community treats each of these exceedingly rare interstellar visits, given how much can be learned from studying material that formed in an entirely different star system, something that would otherwise be completely inaccessible to direct study by any means available to humanity. As 3I Atlas continues its outward journey, already well beyond the orbit of Jupiter and picking up speed as it moves further from the Sun's gravitational influence, astronomers are racing to extract as much remaining chemical data as possible before it fades permanently out of reach of even the most powerful telescopes on or near Earth. Every additional observation session adds further detail to researchers' understanding of its composition, its physical structure, and, by extension, the broader question of what conditions might have shaped the distant, ancient planetary system it originally formed within, long before it ever passed anywhere near our own solar system at all. The methane detection published in April of 2026 likely will not be the last significant finding to emerge from Webb's ongoing observations, and researchers have indicated that additional analysis of the existing data, along with any further observation windows that remain available before the comet becomes too faint and distant to study, could still reveal additional chemical detail in the months ahead. It's genuinely worth sitting with the actual scale of what has been detected here, because the real story, stripped of any exaggerated framing, is already remarkable enough on its own terms. A chunk of ice and rock, quite possibly twice as old as our own sun, formed around a star system that may not even exist anymore in any recognizable form, spent untold billions of years drifting silently through the near absolute zero vacuum between stars, and happened, by pure chance, to pass close enough to our own solar system for humanity's most powerful space telescope to capture the precise chemical fingerprint of its escaping gases. Not once, but across 2 separate observation campaigns using 2 different instruments, each adding new layers of detail to an already unprecedented picture. That is the actual signal Webb detected, an ancient chemical record encoded directly in light, of a place and time in the galaxy's history that no human being will ever otherwise have any way to directly examine, transmitted not through any deliberate act of communication, but simply through the ordinary physics of sunlight vaporizing ice, exactly as it always does on every comet, everywhere, whether anyone happens to be watching or not. There is something genuinely difficult to fully absorb about the scale of time and distance represented by a single, small chunk of ice and dust passing silently through our solar system on its way to somewhere else entirely. If the age estimates hold up under further scrutiny, 3I Atlas was already an ancient, fully formed object several times over before our own sun had even finished condensing. Out of its birth nebula, it has spent the overwhelming majority of the universe's entire history drifting alone through the near absolute zero vacuum between stars, encountering essentially nothing until a chance gravitational trajectory finally carried it close enough to our particular corner of the galaxy for humanity's telescopes to notice it at all. It will spend the rest of its existence, effectively forever, continuing on in exactly that same solitary drift, this brief handful of months spent passing through our solar system, representing the only close encounter with another planetary system it may ever experience across its entire multi-billion-year existence. For now, the explanation stands as one of the more genuinely satisfying results to emerge from the entire body of research surrounding interstellar objects to date, not evidence of any artificial transmission or technological signal reaching us from beyond the solar system, but proof of just how much can still be learned from the simple, ordinary light escaping off the surface of an ancient wandering comet, provided the instrument doing the looking is sensitive enough and patient enough to read exactly what that light is trying to say.